I appreciate you all dialing in and registering for the first virtual session for the VFS workshop on infrastructure for eVTOL. VFS has been looking and leading at the eVTOL revolution since 2013, and we held our first transformative vertical flight workshop in 2014, and have held something in the ways of a workshop or a symposium every year since, including our recently held 7th edition back in January in San Jose. You are able to go to the VFS website and go to the VFS store and purchase the videos and the presentations from each of those symposia and workshops. As we've been leading this and are the leading technical society for vertical lift and have been for 75 years, we started the eVTOL.news website in 2015, and we've cataloged over 260 different eVTOL types, as well as the companies and a lot of other information. And we do send out a bi-weekly newsletter from that website. So if you go to eVTOL.news and sign up for the newsletter, we'll keep you up to date on what's going on in eVTOL. So with that, I'm going to now turn it over to our moderator for today, Mr. Rex Alexander. He is a consultant for Vertical Flight Society for infrastructure and is a leading expert in this space. So I'll hand it over to you, Rex. Mr. Alexander, please.
Thanks, Jim, and good morning, everybody. Greatly appreciate everyone signing on early on a Wednesday. Hopefully you will enjoy everything, learn a few things, and at the end we'll have a Q&A, and we really do want a lot of good questions because that's what's driving our next session, which will be a face-to-face this fall. I am, like Jim said, the Vertical Flight Society's infrastructure advisor and today's moderator. And our first speaker today is a wonderful individual, Teresa Peterson, Senior Project Manager and Vice President with Gannett Fleming, based in their Marlton, New Jersey office, and responsible for performing feasibility studies and providing design and construction phase services to public and private clients. Project experience includes oversight for power transmission and distribution systems, upgrades and analysis, and control building renovations, substations and switchyards, load studies, flood mitigation, and storm hardening engineering and design. Facilities project experience includes elevator upgrades, building envelope environments improvements, utility design and permitting. With over 19 years of experience, Teresa is a member of the American Waterworks Association and American Society of Civil Engineers. And without further ado, I'm going to hand it over to Teresa, our first speaker. Thank you.
All right, thanks, Rex. I hope you all can hear me here. I'm just going to spend a quick minute, give you a little bit of introduction. You heard all about me, and I'll give you a quick slide on Gannett Fleming. Gannett Fleming is an architecture and engineering firm that has provided innovative solutions to our clients' most challenging problems for over 100 years. Focusing on transportation and infrastructure, we are excited to be part of this transportation revolution. As a trailblazer in urban air mobility infrastructure, we offer developers, transportation authorities, and eVTOL operators a design partnership that can help make this emerging industry possible. Our solutions, whoops, too far, one back. Let's see. There we go, well, too far. We'll get there. Okay. So our solutions are designed to be flexible and modular while maximizing safety, sustainability, and passenger comfort. We design with smart components that promote efficiency and integrate into smart cities plans for the future. We're proud to be thought leaders in reshaping our communities for the better. So in the past, I've discussed some of the life safety codes, the HVAC, the electrical and fire protection systems that may affect vertiport designs. In this presentation, I plan to highlight some of the building code considerations. Please note that building codes are adopted by each jurisdiction, and any community may choose to adopt different editions or apply more stringent requirements than the latest IBC edition. The current version of the IBC is 2018. Not all states have adopted the 2018 version, but all states have adopted most parts of some version of IBC. There are about 15 states that have adopted the 2018 version, and that changes every year. There are 35 chapters that cover materials, interiors, life safety, types of construction, elevators, plumbing, and many more. And the important thing to note is that the IBC covers both prescriptive and performance-related requirements. In addition to the IBC, these are some of the other code agencies that may develop prescriptive or performance-based standards for the design of building systems. So whether we are considering an urban downtown core or a middle America suburban destination, the ability to find space for vertiports in desirable locations that can accommodate additional modes of transportation, parking, and mass transit connectivity in our already built out environments will be a challenge. While greenfield construction and brownfield reclamation are desirable options, it's likely that most vertiport networks will include some building retrofits. This is not a showstopper, but it will require careful consideration of the existing conditions and cooperation from owners and permitting agencies, and absolutely flexibility in site selection. Greenfield construction is construction on a fresh, undisturbed site. While the building codes are not yet modified to incorporate standards for eVTOL and vertipads, the building will be designed to meet those eventual standards. So FADOs and T-loft spacing, parking adjacency, passenger terminals, floor loading, fire and life safety systems, and vehicle charging will all be designed based around one or more eVTOL selected by the owner. Evaluating those same conditions and modifying an existing building to meet those requirements will present a greater challenge. So questions like, if a building was built before 1990, it may not meet our current seismic requirements. On October 17, 1989, the Loma Prieta earthquake struck near San Francisco. A 6.9 magnitude earthquake, it caused nearly $6 billion in property damage. And in 1990, the code agencies set to work redefining seismic requirements to reduce the impact of future earthquakes. So if you take a look around and you consider how much of our built environment was constructed before 1990, you'll see that it exceeds the construction in the 30 years since. So start to get into some of the specific IBC sections. According to the 1968 building code, a high-rise structure was any building that was at least 75 feet in height measured from the curb. According to the Encyclopedia Britannica, a high-rise building is any building tall enough to require the use of an elevator. Still, other definitions classify anything less than 115 feet as a low-rise. But since we're following the IBC, per the 2018 IBC, a high-rise must have an occupied floor at least 75 feet above the lowest level of fire department access, and not more than 420 feet, because anything over 420 feet is a super high-rise that has a different set of rules. And from some of the things we've heard about eVTOL operation in urban downtown centers, to reduce wind shear and influence, a vertipad may need to be installed at least 10 feet above the top of the existing rooftop. So if we assume that battery storage and mechanical systems are installed on an existing converted floor somewhere below the vertipad, the decisions about placement of the terminal space, where do you want the passengers gathered? Would it be immediately on top of the roof? Will it be elevated like the vertipad? All of these decisions will affect the height and will be in some way modified and controlled by the building codes. And a quick shout out here to zoning ordinances. While not in the building code, zoning ordinances are written by local jurisdictions to regulate how properties can be used. Things like lot size, building density, noise, and heights of structures are controlled by local municipal governments. The building code suggests how to build safely, but the local zoning will dictate how tall is too tall. So from an IBC perspective, adding additional floors might require modifications to fire pumps, sprinkler systems, alarms, and electrical wiring, and these can all be very costly and may affect the entire building. But they can be worked out for the right price. Navigating local zoning codes may present an entirely different type of political challenge. And if we want to talk about adding height or additional occupied space to the top of an existing building, we look at IBC section 1510, the aggregate area of penthouses and other enclosed rooftop structures shall not exceed 1/3 of the area of the supporting roof deck. So what does that mean for us? If we consider one FADO with, let's say, 100-foot diameter for the flight safety area, and 3 parking charging pads per FADO, a passenger terminal that could easily reach 2,500 square feet, and now we've taken up 16,848 square feet. So the minimum size roof that could accommodate a single landing must be at least 50,500 square feet. So that's a building with a rooftop footprint of around 250 by 200. It's not outrageous, but might be bigger than what you were originally envisioning. Talking about building egress is another important consideration. Building egress, or how we evacuate, is designed based on the maximum occupant loading of the most utilized floor. So when building use or occupancy loading changes, or if the vertiport and terminal loading is greater than the original design, we have to reevaluate the means of evacuation for compliance. We need to evaluate if we can get enough people, the anticipated number of people, out of the building safely in the event something should happen. So items that we would have to look at include the egress path width for the doors and the stairs, the accessibility to those areas of evacuation, areas of refuge where people might have to wait for first responders, and fire ratings of the exit passageways. So just to give you a little bit of background on this, the current code dictates that an airport terminal use an occupancy loading of 100 square feet per person in a concourse area and 15 square feet per person in a waiting area. So if you think about it, when you're about to board your plane, people kind of jam up together a little bit. Everybody gets a little bit closer. You don't require as much space. So the density and loading of that area increases. But it's based on how much of that building is classified as the waiting space versus how much is classified as a concourse area. Compare that and contrast that against a business and professional area which is typically designed for 100 square feet per person, or a residential space, which is 200 square feet per person. So a residential building would be designed to evacuate a lower number of people than an office building, and a lower number of people than an airport concourse or a passenger waiting area. So you can see that a vertiport terminal could require a higher number of people to be evacuated from a space and could require modifications to existing stairways and egress paths. And as we've discussed many invasive major modifications to the building core, one solution you might think of is, hey, let's strap a set of stairs to the outside of the building as a way of adding additional egress capacity. Well, that's maybe okay. So per section 1027, if the building is a low rise or a mid rise, you might be able to do that. It might be a solution you consider. Obviously, this won't work well for a high rise building. Another example where understanding the history of the building comes into play, the American with Disabilities Act was signed into law in 1990. So prior to 1990, it was the decision of the building owner to include provisions for building access for those with disabilities. It was probably a financial decision. But providing ADA accessibility is a federal law. The building code describes how to achieve compliance with the law. So with a renovation project where you're trying to retrofit new facilities into an existing building, there may be situations where complying with the law is just not possible. It's just technically infeasible. We cannot do it. In all other situations, the building owners are at risk for non-compliance. Building code is different from the law. You may be code compliant and not legally compliant. So under the building code, they require that you spend 20% of the cost of a interior renovation project on ADA compliance and helping to bring the building into compliance. But per the federal law, building owners were given 30 years to make their buildings fully compliant, and they don't really have a tolerance for we're partially compliant. So just because you've changed the height of a water fountain or you've added automated door openers to one part of a building does not mean that your building fully complies with the law. And considering that the goal of urban air mobility is to serve a wide range of differently abled guests, an owner may want to improve accessibility to reach a greater ridership. Strategies for improving ADA accessibility include extending existing elevator service to the rooftop, adding additional elevators, providing ramps for minor changes in elevation, and adding restroom facilities to meet the occupancy. All of these solutions include major renovations to existing structures. Let me get too far. Mixed-use buildings are not a new concept. Combining the spaces where we live, work, and play into one space has been part of urban planning since we first started building settlements. But recently, we've seen a resurgence of mixed-use developments to capitalize on the benefits of affordable housing, walkable neighborhoods, better land use, and improved community identity. Fire separations indicate how the floors and walls between each classified space shall be constructed. So spaces with a similar use may be considered non-separated spaces. So what does that mean? That means if you have one floor that is all classified as office space, that the risks to the occupants of that floor are all the same, and you would be protected as one unified space. However, if you have spaces that are adjacent to each other with a different classification, let's say you took one far end closet and decided to store hazardous materials and batteries there, you would want to protect the office space from the hazardous classified space. And those types of classifications may require separation in accordance with IBC 2018 Table 508. So increasing the fire rating of a floor construction is a way to meet minimum separation distances, and you can have separation requirements between floors vertically and within a floor horizontal separation spaces. So horizontal separation might protect a mechanical space and emergency exits from other types of use cases. And if we want to talk about Chapter 16 and some of the structural considerations, an ordinary flat pitched roof that is not an occupied space and not designed to be an occupied space may be designed for 20 PSF uniform live load, while an occupied roof, something like a roof garden or a space where people are designed to assemble and congregate, may be designed for 100 PSF uniform live load. Different places in the country might have additional snow loads to consider. Per the IBC, helicopter landing and parking pads are designed based on the takeoff weight of the vehicle, which is either 40 or 60 PSF minimum per the code. So if we were to take, for example, a 6,000 pound eVTOL distributed over a 1,500 square foot T-loft, that gives us a 4 PSF uniform loading, which would be distributed on top of the roof. But as we mentioned before, due to wind influence, we are not looking to install directly atop the roof. And per the code, I'm not allowed to use 4 PSF in my calculations because IBC is mandating, dictating that I use 60 PSF. So if we consider a steel truss system that might elevate the T-loft, like the picture that you see there, and connect the pad at, let's say, 10 locations, that's 6,000 pounds divided by 10 points of connectivity. If I'm using 8-inch beams, it could give me a loading of 1,350 pounds per connection, which far exceeds any roof rating. So what we would want to consider is maximizing the number of routes and touch points in connectivity to distribute the load over the entirety of the rooftop. Other considerations, the International Green Construction Code is part of the International Code Council family of codes like the IBC and the IFC. The IGCC regulates construction of new and existing commercial buildings to decrease negative impacts of construction and promote the benefits of good design principles. It is a whole building system approach to construction, which focuses on building better indoor environments, lowering the impact to natural resources, and overall improving neighborhood connectivity. And while you may not know, you notice that California is not highlighted green as one of the 14 states that has adopted the IGCC. Rest assured, they do have their own green building standards that apply to new construction and renovations, alterations of existing buildings. It was created in 2007. Cal Green was adopted to address the 5 divisions of building construction, including planning and design, energy efficiency, water efficiency and conservation, material conservation, resource efficiency, and environmental quality. And these are codes that all must be met and satisfied in addition to the strictly IBC codes for building construction and use. So in wrap up, just a few points to remember. Any opinions expressed in this presentation are educated best guesses because the codes do not recognize vertipads as building structures or components of buildings, nor do we have a stable of sample vertipads that have been accepted and built that a code official could refer to. This should not be considered all inclusive. There's 35 chapters. I've only hit on a few of the items that you may want to consider as you're starting to look at different types of buildings for your vertipad network. As the designs for a functional vertiport emerge and evolve, they may trigger other sections in the IBC that were not discussed in this presentation. So building codes are adopted by each state. It will be a challenge to get all of the states to adopt the latest version so that we can take advantage of new technologies as well as eVTOL and vertipad and vertistop standards. Don't forget about the impacts of local zoning on your building selections. And the best thing I can say is that applying new codes to old buildings is really hard. So please be flexible and be cooperative and come with some ideas and tolerance as you're talking with your code officials. That's it. Thank you. And turn it back to Rex.
Teresa, thank you very much. That very insightful presentation on building code principles and some of the challenges that we will be facing in the future, both on new construction, especially on retrofit. That will be a challenge, to say the least. So if you have a question, please, as a participant, put that in the question box, and I will be sure to come back to all those and disseminate those to the right person. And some will be answered by an individual, some will be a group discussion, I'm sure. So our next individual is David Phelan, is a board certified fire officer who previously served 25 years as a municipal firefighter. He currently works in post-incident analysis and fire code development, focusing on fuel dispensing and portable fire extinguishers. He has been published in a variety of industry publications and has extensive teaching experience in fire and building code. In his work performing post-incident analysis, he has testified on a variety of investigative and code matters, which affords him a unique opportunity to take the lessons learned and develop code language which resolves or minimizes future risk. Without further ado, I'd like to introduce you to our next presenter. David, you have the controls.
Thank you, Rex. Good morning. Just looking for my slides here. There we go. All right, so I'm going to focus on the fire code issues that would impact air mobility, similar and in a kind of handshake arrangement to how Teresa discussed the physical structure. I'm going to be looking at the fire safety and fire code requirements. All right. So the first thing to kind of understand going into this is that no matter where we look or go, there are primarily two major building code documents that are published and in use in some form or edition. They're either the ICC's International Building Code or the National Fire Protection Association's NFPA 5000 Building Safety Code, and that's where Teresa spent most of the discussion. Looking at fire safety and operational safety for processes within those structures, we would find those requirements generally in either the International Fire Code or NFPA's fire code document known as NFPA 1. All right, and again, depending upon where we go, in whole or in part or with modification, some addition or some version is likely in effect. And the most important takeaway at this moment is that none of those documents specifically address electric vertical takeoff operations. Okay, we are discussing something today that doesn't actually appear in those documents. And so that raises the first concept or the first question that emerging technologies face when it comes to building and fire codes. And that is, when we're talking about something that doesn't yet exist, how do those codes answer or address that? And the reality is there's three possible manners in which your situation or your emerging technology could be answered in any local municipality or by individual code people. And not to be facetious, but they literally are the answers you see on the screen there. You approach with a new technology or an emerging technology, and they just simply tell you absolutely not. And you're shut out at that very moment. Some may entertain it long enough to listen to what it's about, but still remain skeptical. And oftentimes you're told, when it's in the code, come back and we'll look at it, because they like to work from within the framework of what has made its way through the code process. And just as a quick side story on that, we recently faced this concept with a fuel delivery business model where liquid fuel dispensed to consumer vehicles was being brought to the vehicles in a mobile environment. And when that technology and that business model first emerged, same situation, not contained in any of the codes in effect at that time. And so it resulted in some friction and some, I'll say, push-pull relationships between the business side and the public safety side. Going on through 2 code cycles, we have finally gotten language in there to regulate the activity. So there is a accepted minimum standard of performance. Getting each municipality up to that current code level to embrace that is a different matter. And so in some cases, the approach taken is, look, if we can get a few of these going, that we can show them as examples, that this is what it is. You can come look at it, you can see it, you can literally experience it. That might be enough to get over the initial hump. And I don't know that that is or isn't the best approach. I don't know that it's good for business because it's not uniformly established. But in the meantime, any single event, a mishap, a fire, or some problem can easily derail that effort. So we have to be cognizant of that going through the process. At the present time, we have a couple of key documents that talk about helistop operations on rooftops, okay? Both the IBC and NFPA 5000 immediately reference to NFPA 418, the standard for rooftop, standard for heliports, including rooftop installations, okay? So there is a pathway and there is a kickoff to get to these rooftop installations, but that's focusing solely on liquid fuel operations, okay? And so then when we look into the International Fire Code as a companion to the building code, we find that it prescribes its own rooftop operational safety, and it doesn't even reference to NFPA 418. So we have a building code sending us to an NFPA standard to discuss the physical and the structural elements of a rooftop installation, and the companion fire code doesn't continue that cross-referencing and instead lays out through its own chapter a set of requirements. And while they're similar between the International Fire Code and NFPA 418, they are not exactly the same. And so we can kind of get ourselves in a little bit of a situation where in some jurisdictions, one set of rules are being applied, and in another jurisdiction, other sets of rules are being applied because the code pathway is not exactly harmonized, okay? To visually help you understand this, if you need it, there's just a quick little flow chart here. And the bottom line is, no matter which pathway you take through the building code, through NFPA 1, the International Fire Code, you always end up at rules based on liquid fueled aircraft. And those rules don't mesh with the technology and the equipment that we're talking about in an EV environment, okay? Within the International Fire Code, their chapter or their section for rooftop, helistop, and heliports break out into a few requirements. They have some clear area requirements, essentially as an anti-collision measure. They require liquid fuel spill containment, and we're going to talk about that specifically separately in a moment. Standpipe systems at rooftop levels, that's the firefighting method once we've dealt with the blanketing of the fuel source. Foam protection to deal with that spilled fuel. The IFC requires foam protection without exception. NFPA 418 has a little bit different flavor on that, in that it requires foam protection, but in smaller or lower risk applications, it provides other alternatives and exceptions. That's an example of the disconnect there. And portable fire extinguishers, which we'll talk about separately in a moment as well. So we're looking at this comprehensive protection methodology. However, when you get down to it, almost everything is based on the risk and hazard of liquid fuel aircraft and liquid fuel spills and discharges, okay? And so that just simply doesn't fit into the picture of the EV operation. And so one of the things that we have to do is that has to come to the table is that we have a true evaluation, comprehensive, start to finish, of the fire risks and hazards of the aircraft systems, and the support systems, the structures and the utility infrastructure, the power systems that also go in par with this. Because again, we are truly attempting to write rules from scratch here. In the containment language, you know, we're very focused currently on spills and discharges of fuel, because the idea of fuel cascading through a building subject to ignition is indeed a problem. Okay, but at the same time, if I'm going to build an EV only site, do I really need to be worried about that? And so even attempting to use the current code doesn't work at all with what the technology is being brought to us. The standpipe requirement, which is the secondary firefighting support, the water-based support, is still a necessity. However we deal with the EV aircraft, we still have to deal with final extinguishment. And so the requirement to bring the building standpipe to the roof level would still be applicable in either environment. While we may not have to look at liquid containment, if we're doing a dedicated electric site, we would have to still deal with the hazard of that fuel source. And there's been a body of work and studies and testing done with electric vehicles to understand how to best handle them when they catch fire and how you contain or allow them to burn out. But the dynamic changes between a curbside or a highway event with an electric vehicle to now an EV aircraft on the roof of a building at basically any height, whether it's 3 or 4 stories or 50 or 60 or more stories. Okay, so that is an element that has to be looked at. While the body of work from electric vehicle battery fires and firefighting is understood and being refined, transposing that to a spot in the sky is a different environment that has to be looked at. At present, the portable extinguisher rules for helistops and heliports rely on dry chemical agents with BC ratings. And without getting too off the end on the science of how dry chemical agents extinguish fires, when we look at a BC rated dry chemical extinguisher compared to an ABC rated dry chemical extinguisher, or what is known as a multi-purpose extinguisher, there is a distinct difference there. And the BC rated dry chemical extinguisher is the preferred and actually code specified type for current aircraft operations. And that's driven off the fact that an ABC extinguisher interacts negatively with the aluminum and metallic parts, and particularly the fasteners and rivets on conventional aircraft. And when you have an aircraft that catches fire, or a fire adjacent to an aircraft at a terminal location, we understand that that aircraft is going to be damaged already by the fire, but it's what happens when the agent is discharged and it potentially is carried to adjacent aircraft, either at a terminal or adjacent charging areas. That is the bigger problem, because it's exceptionally difficult to decontaminate the surfaces. So the BC dry chemical extinguisher has been the industry standard for that reason, to protect from the metal interaction and degradation. When we introduce the electric aircraft, do we need a Class A firefighting agent? Will we be experiencing Class A burning fuels? Because if we have a fire involving Class A fuels, plastics primarily, wood, paper, secondary, a BC dry chemical extinguisher is not going to be effective at final extinguishment and prevention of reflash. And so this kind of sets up the scenario, particularly where both types, liquid fueled and EV aircraft, can be co-located, because there's a bit of a conflicting interest there. And so that's a different element that needs to be looked at. We simply can't transpose extinguisher requirements at present to this environment without fully understanding what will be the fuels involved and how will they be burning. Since there are no rules, and perhaps people, participating right now have the ability to influence decisions down the road, here's a couple of other things to consider. And essentially none of this exists presently in the liquid fuel environment. The ability to disconnect power to the equipment on the roof is obviously important. But what is more important is that it can be remotely disconnected from a point anywhere below the roof. We don't want to send the responders directly onto the roof in order to access the disconnecting equipment. We don't know the extent of the problem on the roof, and bringing them onto that level to simply disconnect power could be a problem. Disconnecting power is a way to eliminate hazards to the responders, but in an electric environment, it's also the way to kill the continuing application of energy, which can be further feeding or propagating that fire. So remote disconnection from below the roof level really needs to be looked at strongly. We have technology now readily available to us to bring rooftop level video feeds to the emergency responders, whether it's done wirelessly, and in some jurisdictions they have this capability where they can receive video feed directly into apparatus and dispatch centers while en route, or if the agency doesn't have that capability, the ability to view that video feed from the ground level, from a lobby or from some other fire command center, fire command room on the premise. Because there's a huge amount of information available when you're looking at video feed real time from the level of the problem compared to standing on the ground looking up and just seeing smoke and or flames spill off the top of a building. And this technology is obviously readily available. It just has to be implemented. Depending upon the building that we're going into, an existing building or even a new construction building, the requirements for alarm, general fire alarm and notification to occupants can vary. But the ability to have a voice-based system, or what's known as an EVAX, an emergency voice alarm communication system, where instead of sounding a bell or a horn and we simply convey the message of evacuate, with a voice-based system, we can deliver pre-recorded messages based on area of incidence, and we can address specific occupants in specific areas with direct live messages. And so we're able to give the occupants information on what to do before the responders physically arrive at the floor or area of incident. And when we're in a high-rise environment, the EVAC is generally already present, but in an existing structure or in a low or mid-rise building where an EVAC is not already required, this is something to look at. The ability to give people on the rooftop, in the terminal or waiting area, direct live information versus a generic sounding of a problem. Obviously, there's a need to coordinate with whatever local response agency there is, not just because this is new, but because their current training doesn't spend a lot of time focusing on this. Aircraft response is something generally limited to agencies that either operate on aircraft or airport facilities or have them in their primary area. So we have the potential with this technology now that we're going to be bringing aviation facilities and aircraft related problems and situations into communities that have never had to deal with it before. And so there's more of a need and more urgency there to coordinate what's happening and provide them with the training to understand, not just because it's a new technology, but because it's a new platform that community hasn't previously experienced. And one of the other things, or one of the other areas to consider, is not just fire and life safety from the standpoint of flame, smoke, and heat, is that the code process has begun to come around the corner and also address other needs of fire and emergency medical agencies. And so when we look at how we're getting access to these future service areas on the roof. Well, we could probably put an elevator and we can probably put a staircase in some way, but we need a way that we can accommodate a rescue scenario, because somebody someday is going to fall and need to be immobilized on this rooftop area. Someone is going to have a medical emergency in the terminal. That's just going to happen. And so while we're providing access, we need to also consider and require that there be accommodation large enough for a supine medical stretcher. So as we start thinking now about how we're going to get through this code pathway, this code process, and what pathway to take, we need to kind of lay out not necessarily priorities, but understand that getting to the code resolution is going to have multiple paths, because it's very difficult to lump new construction rules into a code presentation or into a code process and then shoehorn them into existing buildings. Okay, so it's probably beneficial to attack new and existing construction separately but concurrently, because some limitations simply are going to require other steps or other alternatives. And we hopefully recognize that there is absolutely no benefit to applying liquid-based hazard protection in an exclusively EV environment. Okay. Then, running again parallel and concurrently to this, is looking at adding EV capability to an existing liquid-based helistop or heliport. You know, it sounds good because, well, we're just adding more aircraft or different types of aircraft to an existing aircraft facility, but we're introducing an entirely different set of hazards to a facility that was designed for an entirely different set of hazards. And so we need to bridge that together and potentially apply both. Keep or upgrade the liquid hazards to an acceptable level and introduce the protection methods and the protection techniques for electric operations. And one of the questions that will be asked at some point down the road when a presentation is made to put this language into codes is going to be, what is the energy source for these electrically operated aircraft? If there's one type, then essentially we'll have one set of rules to address the hazards. But if there's a potential here that we have multiple different types of energies, yes, they're all electric, but they're derived in separate ways. Now we have to begin to look at specific rules for those specific technologies, because generally they don't all work the same way and the hazards may be different. And potentially, since we haven't really spent any time looking at or testing this, when I develop the electrical energy-based rules and I look to apply them into or co-locate them with liquid fuel-based facilities, is there a possibility that any of those sets of requirements might conflict or counteract each other? I don't know that, and not that anybody does know that at this point in time. You know, you would like to say that, well, everything's for fire and life safety, so everything should work together. We do need to look at that in a co-located facility. So the first steps in this process to getting to the point where you can look at preparing and presenting for code language is everyone's understanding and embrace, not just the people in the industry, but also in the code environment and the code development community, that liquid fuel aircraft operations are distinctly different than EV operations. They may happen at the same location, they may serve the same overall need, but they are different. And therefore, we need to understand that the rules will be different and the approaches be different as well. And unfortunately, we don't have historical data that we can rely upon and that we could say, well, this technology has been in use for X number of years and we've performed X number of flights. Our rate of failure is this. Our most frequently experienced mishap or loss event is this. We don't have any of that to work with, okay? But that will end up being information that is sought as part of the process to develop the codes. So we need to discuss and in many cases test those theories by doing practical fire testing of the aircraft, the shell, the frame. You know, we understand how batteries work and how batteries fail. That information can come over. But if we introduce new energy technology that hasn't been previously looked at or tested, we're going to need to do that as well. And so the means to protect and the methods to suppress and respond to these fires are unknown. And someone is going to have to step in collectively and start looking at that. And we understand that if the energy cells or the battery cells cannot be effectively extinguished and stopped, and the approach is to let them burn, let them exhaust their energy and react to the point then where they are non-volatile, there is a time and energy release component there that has to become part of the design of the facility. If you're going to say, we're going to let this essentially burn itself out, how long will that take to do, and what will be the energy released in peak and over the course of time? Because I need to protect the building from what's happening around it if that's the true approach. So that's my presentation, that's my information, and obviously we'll probably have some questions. Rex, I'll turn it back to you.
David, thank you so much. It's very in-depth on the fire code piece. I got a lot of great questions from that. Again, we're collecting the questions and we'll go through those as quickly as we can at the end. Also, had a couple questions early on as to whether we will make these presentations available, and the goal is to make these presentations available to everybody. We're also recording this, and the question and answer period, we'll put that into a format as well and provide that to everybody at the end of the course. As far as how fast we get that done, as quickly as possible. So that leads us into our next individual, who is our next speaker, Scott Cary. Scott is Ports and Airports Project Manager for NREL, National Renewable Energy Laboratory. As one of 17 Department of Energy national labs, NREL is transforming energy by advancing the science and engineering of energy efficiency, sustainable transport, and renewable power technologies, and provides the knowledge to integrate and optimize energy systems. Scott has more than 20 years of aviation design and construction management experience with the Department of Defense and aviation, both domestically and internationally. As the Ports and Airports Project Managers for NREL, his role focuses upon assisting with advancements in transportation technologies for the transportation sector, primarily ports and airports. Scott is a licensed engineer in multiple jurisdictions and enjoys assisting aviation partners with leading edge implementations of technology. So please welcome our next speaker, Mr. Scott Cary. Scott, it's all yours.
Thanks, Rex. Thanks everyone, and I really appreciate that conversation we were just having. It's very interesting as we start talking about the energy resource discussions and we start to transition into what I call the fuel. Regardless of what material comes in, we need some type of energy to be provided to an aircraft or to a vehicle in order to move, and historically that's been fossil fuels. In the urban air mobility space, there's been a lot of advancements in going towards electric-based and alternative fuels. And we're going to talk a little bit about NREL and talk about what we're seeing in terms of the overall energy picture across the nation and how that's going to impact. What we're seeing is how that's going to impact the future of implementation. Make sure I can move. So what we're seeing is that across the nation and across the world, there's a energy revolution underway. The 100-plus-year-old system is transitioning. And what we're finding is that as traditional sources of energy generation are shifting, and it primarily has to do with cost, is where it currently is. We're seeing natural gas still trending up. We're seeing coal trending down. Nuclear is staying steady. But the trend that we're seeing the most right now is a place that NREL spends a decent amount of time in is non-hydro renewables. It's increasing. And we're expecting the next 2 years to go from 10 to 13% of generation. And non-hydro is generally wind and solar. With that, as you can start to see, is what's going on is that even 10 years ago, the cost for utility grade wind and solar was almost $360 a megawatt hour for installation. We're now seeing in 2019 costs between $36 and $21 a megawatt hour. The cost for coal has remained essentially the same, come down a little bit. Nuclear has actually gone up a little bit with current technologies, and gas has stayed constant. Well, why does that matter? What's happening is that rather than having a fewer number of large generators to manage across 3 utility grids in the United States, we now could have 5,000, 8,000, 10,000 generators that have to be managed, and many of those are intermittent. A cloud goes over for solar. It changes the amount of energy that comes off, say, a home rooftop. That decentralization requires better communications within the system, and we call that digitalization. And then with that digitalization, you have the opportunity to have, we call them distributed energy resources, the batteries, the loads that you can call ahead and say, hey, would you mind waiting a bit to take your energy from the system? We have a lull in the available generation, or now is a great time to fuel up your reserves. Well, okay. My apologies, something happened here with the backgrounds. What's happening within the aviation industry, NREL has been working with multiple airports across the nation, primarily related to power quality and availability, and also improving electrification for some of the early adopters. Just to give you an idea, with the increased demands and the variability in generation and a very old system, power outages are increasing. And if we shift to a single power source in electricity, some of that redundancy that we have related to the fuel sources and transportation now have to be improved. Probably the best way to put it. We see 4 key elements of sustainable mobility that go into this, and we'll go through each of these kind of quickly to give you an idea of how these all integrate. Movement of people, movement of goods, power and mobility, and transformative technologies. And what we have going on is that we talk about movement of people. You start to see that we have a combination of advanced materials, energy storage to look at, how the power electronics work, what materials or other sources are available to support moving those people, such as hydrogen, biofuels, other storage technologies, new battery technologies, and the connectivity of all those items in relation to managing when those loads are requested and needed. One of the items that we at NREL are working on right now is related to, has a very close correlation to what's going on right now with UAM, is megawatt level charging. And it's primarily right now we've got a long-term program going on with the Department of Energy related to heavy vehicle charging and trying to manage the charge rates, the C rates of the batteries and the chargers themselves. Right now, what is happening is that at least current technologies show that the charger can deliver more energy than the battery generally can safely receive without generating too much heat. You have to dissipate that heat and resolve some of those items. As we get into moving goods, it's a very similar discussion. You start looking at how do we increase the capacity of those vehicles, the energy storage, where do you put it? How do you make that all work? To give me an example of some of the things that go into a typical system that we would typically look at and try and look at it kind of on the early adopter or pre-code level is how do you manage that system as a system? Historically, it's been, I just need power. I go to the utility company, say, thank you. There's a new feed that's provided. With the loads that are coming online, there could be years necessary to make the necessary upgrades to get to the locations that you need. As we start to think through that, we start to say, okay, what about storage? And what about the size of the facility and the amount of energy that needs to be delivered? And so storage becomes something to think about, along with potentially even using some of the resources on these diverse locations to essentially stabilize the grid as well and recharge back into the grid. We get into the mobility side of it. We talk about renewables and very similar things, grid integration, cybersecurity, and the extreme fast charging. And what happens in here is we are seeing these trends, and NREL as a national laboratory has been working with partners across the US and world to take on and provide some of the necessary research to bridge from university to implementation for many years. And we started with light duty vehicles and have spent some time with the Department of Defense on some of their heavier vehicles. And right now, the big push is on Class 8 and heavy-duty trucks, which have similar energy loads to urban air mobility. They are choosing currently to go at lower charge rates than what we are hearing from industry within UAM. And that's kind of the next challenge within aviation. The big question is trying to get the energy density up in those batteries is one of the big places we see. Kind of the wave we see coming in, we're calling it the third wave in aviation, is urban air mobility, the pilot training and regional service for commercial service. And then hybrid systems that are currently in prototyping levels with multiple companies that are trying to use or plan to use electricity for takeoff and landing and run potentially on a diesel engine, a diesel generated generator during flight. One item that may be of interest to some in this group is to look at what some of the resources came out of an industry group, workshop we did with the heavy truck industry on this topic. And there's this presentation, there's a link in here to that presentation talking about the fast charging workshop, having people like Cummins and Daimler and others in to talk about what they're seeing with their platforms. And we're working together to try and come up with some better opportunities and potential solutions there. One of the things that has come out of some of this, and this is where it definitely I could see some good benefit, is one of the items that we look at in terms of studies is total cost of ownership And I believe we're hearing that that's one of the reasons that electric propulsion is desirable in UAM. A key element to consider as you're looking at these systems across the nation and installation of systems is, in many cases, you can have availability of energy at a specific location any time of day or night. However, if you do not have a way to manage when you request that energy, you could be taxing the local grid to the point that the grid is trying to manage that by providing increased demand charges. So you can double your energy cost depending on the time of day that you choose to request energy. That then goes back to this question of energy storage and how do you store that energy? There's active work going on right now within the national labs to work with the utility providers and many of these manufacturers of equipment to manage what we call behind the meter storage, and to, you've probably heard some things like choose to run your dishwasher late at night. That is a choice someone can make. Or there's some utility providers that have methods to defer or cycle air conditioners during high load situations. This takes us a step further and tries to not just have prescriptive or rough models, but to actively work with distributed resources, in many cases owned by municipalities and others that are outside of your typical utility providers, to manage loads across the system. So why do we want to do this? An easy way to look at this is, think of the graph on the right here is essentially the daily load profile for, let's just say, a typical city. And it peaks generally towards the afternoon, especially in the summer with air conditioning loads, and then goes back down through the night and then rises again. The ideal situation based on how grid performance works is you want to lower those peaks or shift those peaks, and it's kind of ironic, but right now it's a similar phrase to flattening the curve. You want to spread those out. It makes the generation match the demand and reduces the need for storage. One way that we're seeing to work to potentially balance some of these items is that excess electricity generation, say during the day from renewables, can be utilized to help create biofuels and also generate hydrogen for storage and provide you with cyclical storage. And also pumped hydro is another place where that works. So you use your available energy during the day to store energy in a different fashion than a battery necessarily, depending on what is the best choice for that situation. And then utilize that energy later. And ideally you put it into a form that is stable, long-term stable for your use later. And some of these systems already exist. To give you an idea, the picture at the top is actually an organism that breaks down plastic bottles to create sustainable aviation fuel. And then the bottom half is actually a hydrogen fuel cell. We actually have in the lab, we have another fuel cell from Daimler that's actually running one of our supercomputers. So we have all these great opportunities to distribute out how we're doing energy and different sources of energy and be able to help manage our own systems. With that comes a significant potential for energy system disruptions. And there are we always have, everybody can think about the hurricane that hits the southeast of the United States, takes down power lines. It's a minor threat, but it does occur related to solar flares, and it is a real low probability, but real occurrence. When we get into physical threats, there's the electromagnetic pulse discussion related to large-scale conflicts in the world. And there are cyber threats. The Department of Energy has realized that within this, there are some significant places that need attention, and we're working to try and manage this system. When you figure that half the world's population uses the internet, and it's projected that there's going to be 125 billion devices that are connected to the internet by 2030. Each of those items is essentially its own computer address into a system. And whether that's a ventilation system, a power grid, potentially, a battery storage system, even your cameras at your home. I mean, just to think through that. The malware attack discussion has to do with people that are looking for exploits in those situations to do something they would like to do that may not be what most people would like. Give me an example. If a HVAC control system for a building, say there are 25 air handlers. If that system is accessed, and those air handlers can be cycled, turn them on, turn them off, turn them on, turn them off, they can potentially destroy the HVAC system in the building very quickly. Take a look, if you have a question about whether this is occurring, there have been multiple reports recently occurring that the grid has had different penetrations over the years. And probably the most recent was same day as the Boston Marathon bombing out in the West. There was a portion of the electrical grid that the operators lost visibility to the grid for a few hours. Someone was able to get into the system, and they had no visibility of how energy was flowing within the system. So those are being addressed, and the Department of Energy is taking that very seriously, looking to try and help make these systems work well together and move forward. With that, we talk about the security alongside of the resilience. That gets into the fire code discussions we've talked about. That gets into the life safety requirements for moving people. And in many cases, one of the things that we see is, say you're trying to make this system be not just all weather, but hardened for some of your natural disaster events. And I think of a helicopter pad for a hospital. You need that facility to operate, especially when there are major events. The fuel source and managing that fuel source is a consideration that we'd like to stress needs to continue to be looked at. Some of the lessons learned from recent hurricanes, like down in Louisiana, had to do with backup generators. Great idea to have a backup generator, putting it in the basement below floodplain, assuming that the levee is going to stay up, turned out to be not the best idea for that hospital. And a lot of those concepts continue into urban air mobility if it's considered a critical facility, if you'd like that to keep operating. So as we look at this, we've talked about the cost competitive renewables shifting in terms of the available generation, and where we're seeing is we're calling it the grid edge. This is, we have a residential building in this graphic, but it's very similar to what we're talking about with a commercial building, with urban air mobility, or even a small community. We're seeing the smart meters, the distributed energy loads in different ways that we can manage, and that interaction from the transmission and distribution side into those facilities is going to be critically important to, one, reduce your cost and improve the ability to deliver energy. And we have a few things. There's working across the labs, there is a significant amount of information moving forward related to fast charging. And we partner with multiple national laboratories and industries to, including in this case, Electrify America and ABB and Tritium, on fast charging situations. Last thing we're going to kind of run through very quickly is transformative technologies. As we work through connectivity and wireless charging and big data analytics and deep learning, one thing that NREL is looking at is we worry about efficiency, and we worry about helping people be efficient. So part of that is not just what happens with the power, but how do we efficiently move vehicles and people and cargo around an area. Right now, one of the biggest programs going on, or a major program we have going on, is called Athena in the DFW Metroplex. And what Athena is doing is aggregating available data between the airport and local transportation to look at the patterns and flows of people into and out of the airport. With this group, we have a series of technical advisors and industry advisors that are looking at this along the way, including some that are on the phone today. Really appreciate all the help and advice, providing additional inputs and data to make this move forward. The focus, and we're just now getting out of the early wins and getting the ongoing, is to provide necessary data to help with operations and future planning, including, to give you an example, they're at Dallas, the Dallas airport. They are trying to optimize their rental shuttle buses right now, and they're trying to electrify those as well. So with that being said, they just had a massive shift in their number of operations. And so the first question that came out is, what can we do to provide the level of service we'd like to provide to our clients, to our customers, our passengers, to move efficiently around the system? The modeling is already in place based on their existing and historic data, and shift some parameters within the computational sciences models. And they're able to then use that data to say, okay, we're going to go from 18 buses to 3 for the foreseeable future for the next few months. And as the flight information keeps coming in showing that passengers are increasing, then the number of shuttles will increase. That historically has not been something that's been able to be predictive. It's been primarily reactive. And then past that, it gets into the choice of mode choices and long-term planning, to where potentially you can have fewer facilities or smaller facilities because you're more readily adaptable to be able to manage those queues and methods to move people. To do this, what we're using is it's called a digital twin. We take the information, the live data from the local municipality and transit agencies and Uber and American Airlines, tie that all together, and then we simulate it moving forward. Simulate that moving forward, and then take that data to save and then predict from there. You can see what it then does is gives you some demand forecasts. Last few things, I think we're getting short on time. Just to give you an idea, NREL is collaborating in multiple areas across the nation and across the world, and is primarily focused on energy and efficiency. Real quickly, we have some areas that we see there are gaps and barriers in research that have been trying to make sure people are aware of. Some of those are in progress and working with different partners. We're seeing this increase in electrical dependency. We're also seeing a significant benefit in developing microgrids for survivability. If people would like to talk more about that, we can talk offline. With microgrids, there's a strong, and we see a strong benefit in planning for resilience for key facilities. And that has to deal with some of the things we've already talked about. That continues. Third-party financing. What is happening here is that this is on the edge between utilities and historic municipalities and private businesses, trying to find the third-party financing for some of these energy systems is a place that we're seeing significant work being accomplished, and a lot of effort's been made with Department of Defense and GSA moving that forward. Last time is really trying to integrate data sets across the nation to help everyone move forward. We're finding that the data sets are sometimes difficult to get a hold of to be able to give good informed decisions, and that's moving forward. Last thing we'll say is now we're a national laboratory out to help industry, academia, and government move forward their goals and take things from university into implementation. So we're actively looking for partners on a regular basis, and if there's anything we can help with, we'd love to help. Rex?
Scott, thank you so much. That's a lot of really good information, very in depth, and I think we may have created more questions than we answered in some cases, but we have received quite a few good questions, and I'd like to go ahead and open that up to everybody. What I'm going to do is show my screen here, hopefully. Jim, I may need you to give me those controls, and I've tried to compile all the questions into an easier format to read. Okay, let's see, get the right screen. And then I'm going to turn everybody's audio on here, so everybody, the individuals that were the presenters, will be able to then speak to the questions. So in putting these together, our first question, this was during the building code piece on the fire separation standards. Is that for typical building materials only, or does it contemplate the much higher temperatures that eVTOL batteries burn at? So Jim, if you can help me get everybody online here to speak. Let's see, maybe. Teresa, I'm showing you that you're unmuted.
Yeah, I think I can maybe take a stab at this one. As I mentioned, there's no discussion of eVTOLs or any kind of high density battery storage like what would serve an eVTOL really in the building codes. So I think additional research would be necessary before building code officials and collaborative agencies are going to establish what kind of UL ratings might be required to provide protection and separation of space for areas where we're storing eVTOL batteries.
Dave, do you have any comments on that one?
Yes, just real quick, Rex. It's a whole separate discussion, but the bottom line is the current time temperature exposure curves used to generate fire resistance rated assembly time values. Those time temperature curves are exceedingly outdated based on legacy fuels going back into the 60s and 70s. So the short answer is there has never been any contemplation in the standardized fire rating testing for batteries of any kind. And so if we get into the idea of developing separation standards, it's probably easier to do targeted testing just with the battery environment than it would be to try to change the time temperature curve used in the existing standard test process. That's just my thought. Thank you.
Okay. Question number 2. While Vertipad and Vertistop are not included in the IBC or IFC International Fire Code, the terms helipad and helistop are used. Is there a difference? I'll take this one because I deal with this all the time. Yes, heliport and helipad, or I take that back. Helipad is not really a term that we use. It's heliport and helistop are the 2 terms that we primarily use. International Building Code, International Fire Code, National Fire Protection Association, and the FAA use those terms. When we look at the aviation side, a heliport and a helistop are identical as to the requirements the FAA put forth. They quantify a heliport as a site that may have fueling, may have hangar space, may do maintenance, where a helistop is just a pickup and drop off. In IBC, IFC, they do use these somewhat interchangeably, but most municipalities look at a helistop as a lower risk, and such in that way may have not the requirements put on them as a heliport would be. In looking at helipad or vertiport, vertistop, there's a good possibility that that's the same way we'll look at those as well. That's yet to be determined, and I know that there's some several groups looking at that. Dave, do you have any comments on that?
No, I'll just read real quick the definitions out of the I codes. A helistop is defined as the same as a heliport, except that fueling, defueling, maintenance, repairs, or storage of helicopters is not permitted. So essentially, yeah, a helistop is I don't want to misuse the term, but it's a touch and go operation. That's you're dropping off, you're picking up, and you're done. If you're doing anything else with the aircraft or to the aircraft, that's a heliport under the I code concepts. And generally, yeah, that's the same in the other codes as well.
And then when we kind of split that out and we look at, so what's a heliport and a helistop versus a vertiport, a vertistop, that has not been defined anywhere. And nowhere will you find the term vertistop and vertiport defined. What the difference between a heliport and a vertiport are, no one knows yet, and that's yet to be created. Question 3, vertiports would not be used for helicopters. Well, maybe not. We don't know yet. That's a good question. We talk about mixed uses, and when you look at the business cases that are in front of a lot of people, they're looking at having a facility that is open to more than just one vehicle so that they can maximize their profit margin. But there are those that are looking at specifically locations that are only used for vertical lift and takeoff vehicles of only electric or something along those lines. Also on the facilities, I assume the requirements to do a security and passenger screening still apply with the secure area. Up in the air a little bit at this moment because most Part 121 operations into and out of airports require TSA screening. Part 135 operations aren't as stringent in that space, but there will definitely be some type of requirement. How stringent that will be, we don't know yet. More to come on the security part. Also, how do you handle luggage if eVTOL packs are connecting to airports? unknown at this time. It'll be dependent upon how much an aircraft can carry. You may have to actually purchase a second seat to carry luggage. I've seen some which are looking at picking the person up with the vehicle, sending luggage by ground. A gray area at this moment as far as what an eVTOL can handle as far as both passengers and luggage. Question 4, how long is a fire code cycle? Dave?
So the international codes operate on a 3-year cycle, 3-year revision cycle. The NFPA 408, Rex, is that you're on a 5-year revision cycle currently?
Correct. 418 is a 5-year cycle.
Yep. And I believe NFPA 5000 is also on a 4-year cycle, 3 or 4. So you're looking, generally speaking, it's between 3 and 5 years, and the building and fire codes are generally the same edition years, but there's no necessary correlation between the I codes and the NFPA codes. Their cycles are constantly overlapping. Can I just add one more point to that question?
Go right ahead.
So the answer is, yes, that's the cycle of publication and through the organization. How a municipality or a jurisdiction adopts is an entirely different matter. Just because the International Code Council or NFPA put out a new edition, it may take years, and in days gone by, it took decades sometimes to catch up. More and more jurisdictions, at least in the United States at the state level, are coming online in a 3 to 4 year adoption process, where they generally lag 1 to 2 code cycles behind. That's not a guarantee, but you shouldn't necessarily confuse the current edition with the targeted jurisdiction you're looking at. There can be some great disparity there. Thank you.
No, I appreciate that. So our next question, given your experience, how would the aerospace industry be interacting with these regulatory bodies to start socializing these new technologies and update the regulatory language? And how long would you foresee these processes taking? Scott, let's hear from you. What do you think on that?
At least we look at the utility providers as a starting point. Right now, their process is 5 for a significant upgrade in available electrical energy. Could be 5 to 10 years from the time you request, if you're trying to make a significant change. And that is from the time you apply to say, hey, we have enough of a load that may need a new substation in this area, until it can actually be implemented. That doesn't even get into the code side of that. From the code perspective, I think between what we've been trying to monitor and see where things are progressing, we're seeing a lot of interaction between the General Aviation Manufacturers Association, Vertical Flight Society, the FAA and NASA, all working together on the vehicle side, and also trying to push forward the system. It feels like there needs to be some test cases similar to what has been discussed before, to be able to show that the systems work, to then help with the code officials to be able to say, yes, we can agree that we're going to adopt these new codes. That could take a little bit of time.
Yep, no, totally agree. And in that space, the Vertical Flight Society is really pushing the envelope to encourage more people to be at the table having the discussion. Online today, we have several people online that are from the Federal Aviation Administration, as well as the National Fire Protection Association and other code agencies. So we're trying to make sure that we are pushing that envelope, getting as many people involved so that we can move forward together and socialize this as quickly as possible, because policy always seems to lag technology. Okay, question 6. How long does it typically take to publish fire codes for new technologies? Dave, what do you think?
Well, the codes are published, revised and reissued from the organizations, like I said, on the 3 to 5 year cycles, depending. But the truth is, how long it takes you to get a new technology in is it's a non-specific time frame. You might be able to get introductory language into an edition, and then over the next several cycles revise it and tune it to suit the emerging implementation. And in other cases, you may make presentations or proposals rather for adding code language and carving out this concept, and it is turned back for 1, 2, or more cycles. It's exceptionally fluid and non-specific. It really comes down to how big of a bite you're taking each time, and how comfortable you can present the topic to answer the concerns about risk. Thank you.
Thank you. Teresa, any insight on what you've experienced as far as getting involved in this and when it comes to technologies and the time frame?
Yeah, a lot of what we do is just trying to apply existing technologies and using what's already in the codes to the best of our ability. Trying to get new materials of construction or methods of construction takes a long time, and it's often easier for us to try to find an alternative on our side than to push through a new code.
No, gotcha. All right, moving on. Question 7, see, that's the same question. Question 8, will the fire protection rules for eVTOLs be easier, cheaper to fulfill compared to the requirements to a heliport? That's a very good question. It's a double-edged sword, in my opinion, because when we look at the fire protection for a heliport, it's primarily directed around the aircraft having fuel and having a fire suppression system for rooftop systems, and then fire extinguishers, and then for ground-based systems, just the fire extinguisher. Then it comes to the egress requirements. The egress requirements will still be the same, but for the electrical systems, what will that encompass? What do you do when you have a full-fledged runaway lithium-ion battery on a 25-story building, and it takes 24 hours to extinguish that safely enough where you can actually move the vehicle? That's going to be a challenge. Dave, your thoughts?
I'm actually going to take a safe, fast exit on this and say I can't tell you what the cost is until we know what the rules are.
Yeah, that's true, and that's why we're trying to come up with the rules now. Teresa, any thoughts?
Yeah, until we know what the rules are, what the requirements are going to be for how people think they can mitigate the risk, I can design a whole bunch of things that are going to cost a wide range of, cheap to super expensive. And, it's not for me to decide what's an acceptable level of risk. That's what we're going to look for the ICC and those types of agencies to help us, make those determinations.
Nope, totally agree. If an owner were to build a rooftop vertiport designed for only EV, use what would prohibit a fueled airship to land on that pad? The FAA doesn't get into this like ICAO does. ICAO has a lot to say about fire protection and fuel and things like that. The FAA points to NFPA and fire code and building code. So this is kind of a municipality piece, more so than it is an FAA piece, at least at this time. Dave, your thoughts?
I kind of had run this through my head because one of the situations that comes up is, people that utilize equipment or systems beyond what the original intent was. And so what if I put an EV pad on a roof of a building or even on the ground, and then somebody brought a liquid fueled aircraft there? Notwithstanding the ability to carry the load and the space to physically do it, I'm guessing that these locations, that these EV only types of facilities, need to be, I'll use the term licensed or approved in a way that clearly designates them that this is purely an EV operation versus a liquid operation, or quite frankly, a co-located operation where it is authorized to do both. Because otherwise, how do I apply rules without any kind of regulatory measure? And that's not even considering an emergency. If there's a liquid fueled helicopter having an in-flight emergency and there's an available EV pad, you do what you got to do. But there would probably need to be a regulatory mechanism, just like now helistops and helipads get FAA approval or recognition for certain type, size, and class of aircraft. We would probably need to look at a way to differentiate EV from liquid, or EV and liquid being co-located legitimately. Thank you.
No, agreed. So we're running out of time, but I have a lot more questions here than we have time to answer. So our promise to you is we will make sure that everyone was asked a question. We will put that together and we'll circulate that amongst our panel members, and we will publish our answers at a later date. I think we have very popular. We have like 24 questions in the hop right now. But we will do that and get that out to you, and we'll make sure that we open this up for discussion, because that's the whole reason we're doing this, is to make sure that we can solicit information from all the people that are involved so that we can come up with the best answers as possible. Jim, you want to have some closing words?
Certainly. Thank you very much, Rex, and Scott and Teresa and Dave. Outstanding job on a great webinar. Let me just get the screen back in my hands here. So just, oh, that's not what I wanted. Definitely not what I wanted. It's funny how I click something and that's not what came up. There we go. That's the one I wanted. So thank you all for taking extra time out today. Reminder that we have tons of resources on eVTOL that gets updated daily, if not hourly, as well as we will have our second virtual session next Wednesday, April 22nd, starting at 11:30 a.m. That session will be on weather systems. And if you haven't registered for that, please go to our website, vtol.org/infrastructure, and sign up for that. And I hope everyone stays safe and healthy, and look forward to our next interaction. So thank you very much. Have a great day, and goodbye.